collapse on itself. So anyway, which one of those you want to believe, it's up to you. All right, so now we have the galaxies. But I think we want to talk about stars, because stars now are very, very important. They have an importance that most people don't know. For example, if it wasn't for stars, you and I wouldn't exist here. Okay, the stars, let's go back. What a star is very simple. It's a thermonuclear reaction where 4 hydrogen atoms are being put together to make 1 helium and release all of this energy. Now, classification scheme. I looked about a lot of classification schemes of stars, and I always picked the easiest one. And the easiest one had 4 different flavors of stars. The flavors were flyweight, lightweight, middleweight, and guess what? Heavyweight. Had to be put together by a boxing fan, just had to be. Now, the unit of measurement used to determine which of those categories you're in is the amount of mass in our own sun. So they have what we call a solar mass. And the way it works is the flyweight stars, the little ones, are those that are less than 1/2 of a solar mass. Then the lightweight stars would be from 1/2 up to about 4 solar masses. Now note, our sun with 1 solar mass is down at the short end of that thing. So our sun is actually a fairly small star. Then the middleweights would be from 4 solar masses to about 8 solar masses, and then the big guys would be anything over 8. And how big they get, I read an article recently where they were talking about a star of 100 solar masses. That would be really, really pretty big. Now, here's an important point, too. These are fires we're talking about. We're talking about burning hydrogen and turning it into helium. Now, I don't care what kind of a fire it is, whether it's a fire in a star converting hydrogen into helium, or a log in your fireplace converting the log into heat and ash. A fire is a fire is a fire. Eventually, it's going to go out. So in other words, stars have lifetimes, life expectancies. The question is, of those 4 categories, which one do you think would last the longest? Well, no, this is a question I always ask my students, and invariably, they always pick the big one. Matter of fact, that's the one I picked too when I was a student. It just seems so simple to me. With all that fuel, it's going to take an awful long time to burn it all up. Well, that sounds good, but that isn't the way it works. Apparently, the big stars have a lot of fuel, but they burn it at a very, very high rate. No, it turns out the smaller you are, the longer you're going to live. For example, those little flyweight stars, it's estimated that the minimum age for those, minimum now, would be something on the order of 50, 55 billion years. Well, note the universe has only been around for 13.7. So that means that any flyweight star ever created is still there. They haven't had enough time to go by to have any of those guys die. To give you some idea, our sun is given a life expectancy of about 10 billions of years. The astronomers say it was created 5 billion years ago, so our sun is now coming into midlife. About 5 billion years to go. Those big guys, those big ones, 100 solar masses, they might not even last 1 million years. So that gives you some idea of time. But I think probably how they die is more important than how long they live. How are they going to die? Picture the core of this star now. Most stars spend 95% of their lifetime in what is called main sequence. Main sequence means you're burning hydrogen, you're converting it into helium and releasing all that energy. But know what's happening down in that core. You're taking hydrogen atoms, atomic mass 1, you're converted into helium atoms, atomic mass 4. So you're making more massive atoms out of the light ones. Well, again, Isaac Newton taught us that the gravitational force is a function of product of masses. And so the idea is down in that core, as it becomes more and more enriched in the helium, the core starts to collapse on itself and starts to heat up and is heading toward what is known as a white dwarf. Now, the white dwarf, the white stands for the fact that the temperature is white hot. So it's a temperature thing. The dwarf part refers to the size. It's estimated a typical white dwarf might be the size of our Earth, so about 8,000 miles in diameter. In the case of the flyweight stars, remember now, none have died, but they say when they do, that's the direction they're going to go to. They're going to go down to a white dwarf, and then finally all the fuel is going to be burned up, and they'll just sort of go out, nothing spectacular there. But what happens in the other 3 is much different and much more important. What's going to happen now is their cores start to collapse down, generating enormous amounts of energy. Remember now, there's more star stuff around the core of these stars, and it gets blown out perhaps 100 times the original diameter of the star. Now we got a giant star, And now the temperature on the outside cools off a little bit, the red heat. So we have the red giant phase of star evolution. Now, the important thing in the red giant phase, think about that core now. A lot more energy in the core. Up until now, you've been converting hydrogen into helium. Now helium starts to be converted, acting as the fuel, into bigger atoms. The biggest atom, as I remember, can go out on the periodic table to atomic number 26, which is iron. But the two I'd like to comment on, carbon and oxygen are created during the red giant phase. What's the importance of carbon? All life as we know it. You and I are carbon products, you see. We're carbon products. Just think about this now. Every carbon atom in your body and in mine was created out there in the red giant phase of a star's death. That's pretty awesome. Oxygen. Now, I always bring this one up because I remember so many students always say they think oxygen is created by green plants. Well, no, not quite. Not quite. The way green plants work is they take, of course, water, carbon dioxide, in the presence of chlorophyll, catalyst, and the energy of the sun, and they convert it into sugars. Now, if you look at the chemical formula for sugar, and you look at the formulas for water and carbon dioxide, in the combination of carbon dioxide and water, there's more oxygens than in a sugar molecule. Well, in other words, when they make that sugar, they got oxygen left over, and they got to get rid of it, and so that's the oxygen they give up, but they do not create it. Every molecule of oxygen you breathe into your body and I breathe into mine is made out there in the red giant phase of a star's death. Then what's going to happen? Well, then they say it's going to collapse on itself, this red giant, very, very rapidly, and as it collapses down, it's heading toward the white dwarf. Now, in the case of stars like our sun, and maybe in the smaller middleweight stars, that's probably what's going to happen. It's going to collapse down to the white dwarf, and then the white dwarf is eventually going to burn out. But what happens to the other one, the larger middleweight stars, and certainly to the big guys, what's going to happen is they're never going to get that far. They're going to crush down, the energy will be so extreme, they're going to explode and form a supernova. Now, here's the importance of a supernova. All of the other elements that we know, natural elements, are going to be created during the supernova. And if from your chemistry, you remember there are 92 natural elements. From number 1, which is hydrogen, to number 92, which is uranium. All the ones beyond that on the periodic table, those are all created as a result of nuclear reactors. They don't occur in nature. But 92, all the 92 elements are created. Most of which, many of which at least, are going to be used to make the rocks and minerals. But here's the point I'd like to make. As an undergraduate, I was a chemistry major. I got my undergraduate degree in chemistry. All the chemistry courses I ever took as an undergraduate, and even the graduate courses I took in chemistry, not once did any instructor ever tell me where the elements came from. I had a course entitled The Periodic Table. I had to memorize the periodic table. I had to know every element and everything about it, but never once did anyone ever tell me where they came from. Where else but a course like this would you learn that? So there's where they come from. They come from the deaths of stars. Then what happens, what's left over from those big guys? Well, it depends. Depends upon how much mass is left down there in the core. Could collapse down to the point we form called a neutron star. Picture this now. The crush is so great that electrons get forced into protons, making, of course, a neutron. That would be a neutron star. On the other hand, you can crush down so far that the thing gets so massive, the force of gravity is so great, nothing can be released from it, not even light. And that's how they think black holes start. So anyway, there's your theory. Then what happens? Well, the end product, of course, is going to be the remains of all this stuff. All these dead stars are going to be blasted out into space, into the cosmos, which is just a fancy word for space. And we're going to create cosmic dust. What's cosmic dust made of? Well, it's made of all the products of those deaths we talked about. There are going to be bits and pieces, for example, of metals, because there's a lot of metals being created. Here, a little bit of trivia for you. I love trivia. Bit of trivia for you. The most abundant single metal in the universe, metal now, is iron. So you got bits and pieces of iron out there, probably copper and all the rest of them. Elements like to get together to form minerals, so there are bits and pieces of minerals out there. Minerals like to get together to form rocks. There are bits and pieces of rocks out there. Now you put those together, that sort of mixture, those are all very dense things, heavy and dense. Well, the density of all that probably averages about 6. But in addition to that, remember, you had an enormous amount of gas. You had all that hydrogen left over. You had oxygen being created. You had helium. You had all carbon dioxide, things like they get together, carbon with hydrogen to make methane. So you had lots and lots of gas blasted out there into the cosmos. But remember now, the temperature out there in the cosmos, what is it, 2 degrees above absolute. So when this gas goes out, it freezes into bits and pieces of ice. So we have what we just referred to as the ices. And the ices are simply bits and pieces of all those gases. Now it's all mixed together and forms this stuff we call cosmic dust. Cosmic dust now fills all the space in between all the stars. So that's what's out there, that dark matter we talked about. Basically, that's what that is. It's cosmic dust. So note we have then a mixture of very dense materials, the rocks, the minerals, and the metals. And then we have the very light materials, all those frozen gases, all mixed together in the cosmic dust. What's the importance of cosmic dust? The importance of cosmic dust is that's where the planets come from. And that's what our next topic is going to be. How are the planets created like Earth? Stay tuned. That's the next topic.